This is, whoa. This is how we do a Unit 6 E2 problem. It is a vertical force. Something that we want to remember with vertical forces is that an object with mass just sitting there in a gravitational field, so basically wherever, because gravity's infinite. If an object is just sitting on a table, it has a weight. You can step on a scale and you have a weight. Congratulations. This weight is equal to mg, where m is the mass of the object, and g, oh g, that's our good old 9.8 meters per second squared. Now, when we did projectile motion, we always put a negative in front of this. We're not going to do that. We only put the negative in there for projectile motion, if you remember, because we always called down or inward to the center of the earth the negative direction. We always called up positive. With forces, we get to choose what direction we'd always like to be positive or negative. We could have done that with projectile motion, but it was just easier to always do the same thing. With forces, though, things can get a little weird, and we are going to use our free body diagram in the arrow to designate is it positive or negative. So if I chose this to be going down as a negative value, that's how we could pick the negative up. But if I wanted it to be positive, it's a positive value. Okay, so just be aware of that. Always just use the 9.8 for g in the weight. And the reason why this weight equals mg is weight is actually a force. If we think about this, F equals ma, a force is a mass times an acceleration. Well, the force here is weight. It equals the mass, and the acceleration is the acceleration due to gravity. W equals mg. Okay, we're going to need to know this because it's going to come up in all sorts of vertical problems that we can do. A vertical problem that we can take a look at here is, imagine for a second that, I don't know, you get ACL reconstruction surgery and you're stuck in an elevator because you can't walk up the steps anymore. So you are in an elevator, beautiful elevator, and if you've ever been in an elevator, and of course you have, you know in the beginning whenever you start to move, you get that little like lurch in there. And what I like to do is I like to walk around in circles in an elevator. It freaks people out, but that's their problem. But whenever you walk around in a circle in an elevator, you get like a sense that you're being like pulled down in the beginning. It's kind of a neat effect. So what we're going to look at here is if you are in an elevator, what would the apparent weight, what would you feel your weight as if you're going up? Now remember, for this box here, it has a weight pulling down. If it's just has a weight pulling down, that means it's actually going to fall through the desk or the table or the ground or whatever it's sitting on. Remember, this desk or table or whatever is actually also pushing up with the same amount of force, and this is N. This is our normal force. Now it doesn't have to be a normal force if you have an object that's like hanging from a rope. In that case, it'd be called a tension, but it's this balancing force here. And this normal force, this, or a tension, is actually your apparent weight. Whenever you step on a scale, it gives you a value, but if you bounce on the scale, you're like pushing down more and then you're like lifting up, the scale is actually giving you a reading of the normal force. It's that pushback. So that is your apparent weight. That's what you're actually measuring. You can't change your weight. You have a mass. Gravity on Earth is this thing. Your weight is what it is. When you bounce on the scale and you get different values, that's because it's not measuring your weight. It's measuring your apparent weight, the normal force. So let's measure that normal force kind of here. We can do that. Let's see. Let's get the elevator to go upwards. Okay, so let's imagine that this elevator is going upwards. Let's say it accelerates in the beginning at a value of 2 meters per second squared. So it's just going to accelerate upwards. You are standing, you're a green person now, in the elevator, and you normally have a mass of 70 kilograms. We're looking for, what do you feel your weight as now? Okay, what is your apparent weight in the elevator? So if we wanted to do this, a lovely and very helpful way to do this is to draw a free body diagram, okay, because there's a few things going on here. What we need to recognize to start off is, if we're looking at you here, here's you. You've got two forces acting on you. You have a normal force pulling up, okay, that's what's causing you to accelerate, and you have your weight acting down, okay. Notice here that I drew weight a little shorter than the normal force because you need to accelerate upwards, and your weight here equals mg. In this case here, your normal force doesn't equal mg because we're also accelerating upwards, okay. So what we can do here to find your normal force, what you're actually feeling that your weight is we can set up Newton's F equals ma equation, his second law. We know that F equals ma, and since we have two forces here, we get to choose the positive and negative direction. Do you want up to be positive or down to be positive? It doesn't matter what you choose, just be consistent. I'm going to choose, just for argument's sake, up to be positive, down to be negative. So when I write this out, I get that the normal minus the weight, normal is positive, plus the negative weight, n minus w, equals ma. What I can do now is, if you wanted to, you could start plugging in some numbers to try to find the normal force. I'm going to leave everything as a variable for a second because I think it's a little easier to move some stuff around. If I'd like to solve for the apparent weight, what is that normal force? How heavy do I feel I am? If I'm looking for n, let's get rid of w for a second. So I'm going to get n equals ma plus w as I move that w to the other side. And if I rewrite w, remember, w equals mg. So what I can really write here is that n equals ma plus mg. And since both of these have a mass term in it, and that's the mass of u, you can actually pull a little bit of algebra and pull that term out of that side. So you have the normal force equals the mass times the acceleration of the elevator plus the acceleration due to gravity. In this case, we know our mass was 70 kilograms. We know the acceleration of our elevator. It was a positive 2 meters per second because we chose the up direction to be positive. So when this is accelerating upwards, that's a positive direction. So we've got positive 2 and then plus our 9.8 meters per second squared for gravity. Okay, if we do this, this is going to be 70 times 11.8 kilograms times meters per second squared. It's going to give us newtons. If we do 70 times 11.8, we get 826 newtons. If we were to actually just take 826 newtons and say, like, okay, how heavy would you feel, like, if this wasn't in an elevator, like, how heavy is that? 826 newtons as a weight, which is mg, so this is like what you would be weighing. If we divide 826 divided by 9.8 for g, you would feel like you were 84 kilograms. So just by having the elevator go upward at 2 meters per second squared, you put on 14 kilograms or 28 pounds. Luckily, the elevator is going to slow down eventually, and you're going to shed that weight. Okay, so that's just a way we can do a vertical problem. It's very similar to the horizontal problems. We set up a picture, we draw a free body diagram, we choose positive and negative directions, we run F equals ma, and then from there it's just an algebra game. And if we can do that algebra game, we'll be set there. Okay, so that's how we can do vertical problems in the unit of forces.